Welcome back. In session 4, we look at the cost function, an important concept in machine learning. We look at cost function as applicable to linear regression. Look at the figure. This is, in essence, the schematic diagram of machine learning problem solving. We have a training set. The training set is from the past data. For example, suppose you are trying to find out a linear regression model for rains occurred in a month, in a particular day, then what you can do is the quantum of rain is the y, the response variable, and the day is the independent variable x. So the training set consists of, in this case, two columns. The first column is the day, and the second column is the quantum of rain, maybe in millimeters or centimeters or inches. So we have a learning algorithm. For the simple linear regression, we use a simple model, linear model. Okay, so that's the hypothesis. The hypothesis is the rain will depend on the day. Okay, so the day is x and the rain, quantum of rain is y. So the hypothesis connects the independent variable with the dependent variable. So our hypothesis in another case may be marks obtained with hours of study by a student. There is a relationship between a student getting marks in an examination based on hours of study he puts in. Here xi, the x corresponding to ith student, x1 for first student, x2 for the second student, and so on, denotes the independent variable, that is the hours of study of the student. yi denotes the marks obtained by the student. So there is a one-to-one correspondence between the xi and yi. Each student has the number of hours of study and the marks obtained, the pair. Okay? A pair xi yi is called a training example. Suppose there are 50 students in a class, we will have 50 sets of xi and yi. So such a data set is called data set. Okay, that is the data set we are going to use for learning. What are we trying to learn? We try to learn the relationship between the hours of study and the marks obtained by the student. So if there are 50 data sets, if there are 50 examples in the data set, then m is equal to 50. That is the size of the data set. So regression is a supervised learning problem. Our goal is to learn a function h. Okay, what is learning a function x? See, by intuition we know the simple linear regression can be described by an equation y is equal to b naught plus b1x plus epsilon. So that's the function. What is learning the function? See, b naught and b1 are unknown. So after the study, we will get the values for b naught and b1. We will get the appropriate values for b naught and b1. Then we can say that we have learned the function. So x drives y. H of x is nothing but y. It's a good predictor for the corresponding value of x. Okay? For historical reasons, the function h is called hypothesis. If the h of x or y is a real number, then it is a regression problem. And if it is a discrete number, a discrete value, then it is called a classification problem. Now let us look at the model. We have already seen the model, but we will explain more in this slide. So y is equal to b naught plus b1x plus epsilon. So epsilon we don't try to calculate in every example. So we only worry about b naught and b1x. B naught is the intercept and b1 is the slope given by rise by run. B naught and b1 are the unknown population parameters. What do you mean by population parameters? See, every real life problem has large data set. So it's so huge that you can't use it for carrying out any analysis. So it's really practical to use the entire population data. So we take a sample from that, random sample from that, maybe 100 or 50 and so on. Then we try to analyze the problem. We try to learn the problem. We try to find out B naught and B1 for the sample. See, whatever you get for the sample will hold good for the population also. So learning or machine learning is essentially estimating the coefficients. It is called parameters in the area of machine learning. It's called coefficients in mathematics. So you draw a sample for the population of interest. In the case of the marks obtained, suppose there are 10,000 students and whose hours of study and the marks obtained are available in a particular subject, then that's the population. From that, you take a sample and using the sample, we analyze. So these are, look at the y-axis. I mean, there are 5 examples given. Not 5, it's more than 5. So the first one, the same marks are obtained. For the same hours of study, there are 3 different marks obtained by the student. The second vertical line, there are 2 different marks were obtained for the same hours of study. And so this is the graph of the marks obtained by the student y corresponding to the hours of study. So this kind of problem may occur in practice where the y is not unique for each x. It can be multiple values. It may not be also. Question is, what should we consider a good line? Basically, what we are trying to do is, we are drawing a line to generalize the problem, to generalize the model. So we know the model, and we want to generalize, see the equation b naught plus b1x is that of a straight line. So we draw a straight line, and we want to ensure, or we want to make sure that this represents most of the data points. So what should we consider a good line? There's another line, there are 2 more lines. Which is the best line? They all pass through the data. So we will find an answer very shortly for this problem. A good line is one that minimizes the sum of squared differences between the points on the line. See, the next slide will make it very clear. So here there are 4 points. 1, 2 is xi, yi, x1, y1. And 2, 4 is x2, y2, and so on. So the x-axis is the hours of study, for example, and the y-axis may be the marks obtained in tenths, for example. Okay. So now we have to find out a line which minimizes the errors, because we make a line, then we assume that rule holds good for this problem. So then you give a value of the hours of study, you get the marks. Okay. So that is the regression problem. Okay, that's a regression line. Okay, let us try to, in the slides following, we'll try to find out the best line which will describe the given data set. So let us draw 2 lines and compare the 2 lines in terms of the error. There is one line. So the first example is 1, 2. That is the first training example, and we project it to the line which we have proposed, the proposed model. Okay, when we project it, the point cuts at 1, 1. So there is an error. Okay, The error is 2 minus 1 whole square because x is same in any case. And y only, but the actual is 2 and estimated is 1. So the error is 2 minus 1. We square the error. If you don't square the error, some errors will cancel out, plus or minus will cancel out, and we get a wrong inference. So we square the differences at each point. Look at this 2 comma 4, the second example, and this line, this point when projected meets at 2 comma 2. So error is 4 minus 2. The whole square is the squared error. Similarly, the third point 1.5 minus 3 whole square, and the fourth point it is 3.2 minus 4 whole square. So sum them up. See, we found the squared difference and sum it up, we get 6.89. This is called sum of squared difference, sum of squared errors. Let us draw another line. The second line is horizontal and project again to that line for each point. Okay, so the errors will vary. Let us look at it. So the errors are varied and we get a total error of 3.99. For example, the first point is 1 comma 2. So that one, when projected to the horizontal line, it leads to 1 comma 2.5. Isn't it? 1 comma 2.5. So the error will be 2 minus 2.5 whole square. So the second point, it is 4 minus 2.5 whole square and so on. So you get the total sum of square difference as 3.99 in this case. The first case, when we drew a line which is slanting, we got sum of squared errors is 6.89. In this case, we are getting 3.99. So the horizontal line, although it looks very odd, that tries to approximate the model based on data points that is available. So the smaller the sum of square difference, the better the fit of the line to the data. This is what you should note. So we should try to always minimize the sum of squared errors in such a way that it is the least. So you keep choosing B0 and B1, different B0s and different B1. See, each line has got different B0 and B1. So you choose the B0 and B1 and find out the sum of squared differences. So the least squares method, this is called the least square method because we try to find out the squares of the errors and we choose a line or choose a model that corresponds to least squares. Minimum, okay? Minimum of the errors. The least square method will produce a regression line, okay? It's important to assess how well the linear model fits the data. So that is assessed by the sum of squared errors, okay? So in sum of squared errors gives a good indication, the right indication of how well the model fits the data. The sum of squared errors is the sum of differences between points and the regression line. See, the regression line is the one which we choose. The points are already there, past experience. Okay, we try to find out by choosing a particular line what is the sum of differences squared. It can serve as a measure of how well the line fits, or how well the model fits the data. The SSE is defined by the y hat means the estimated value of yi minus yi the whole square, and you take it for each point. So there are m training examples. I is equal to 1 to m. Yi hat minus yi whole square gives you the sum of squared errors. M is the number of training examples. So we should now learn what is the cost function. So we can measure the accuracy of a hypothesis function by using a cost function. What is the hypothesis? Our hypothesis, a generic hypothesis, b0 plus b1 x is equal to y. So then we find the value of b0 and b1, or we assume the value of b0 and b1, and we get a known hypothesis. So then we have to find out what is the cost of this, or what is the error associated with this hypothesis, this b0 and this b1. So different b0 and different b1s will give different sum of squared error. So the cost function is nothing but the sum of squared errors divided by 2m. So we denote it as j. cost function is known as j, it is slightly different from sum of squared errors. We try to make it, rationalize it. So j theta naught theta 1 is the sum of squared errors divided by 2m. So y hat is nothing but h theta xi. For each value of x, whatever is the yi you get, that is the first term, and actual yi is the second term. So divided by the whole thing squared divided by 2m gives you the cost function. The cost function is otherwise called squared error function or mean squared error, MSE. We saw SSE where we find the sum of squared errors, and mean squared error we get by dividing by twice the number of 10 examples. We are using 1 by 2 as a convenience for the computation of the gradient descent, which we will discuss later. Because it's for only for convenience. You could as well use 1 by m. Normally MSE is defined as the sum of squared error divided by m. But in machine learning we use 1 by 2m only for the sake of convenience, which will be clear in the next few slides. So the cost function obtained for a particular given problem, maybe it is the marks obtained by the student and the hours of study, and we assume theta naught and theta 1, different theta naughts and different theta 1s, and compute the cost function j theta. So there are 6 rows, so 6 different sets of theta naught and theta 1 was assumed, and the cost was calculated. So for instance, when theta naught is 2 and theta 1 is 1, you get a cost of 40. When theta naught is 4 and theta 1 is 0.6, you get a cost of 2. So the golden rule of thumb is choose the theta values which minimize the cost function. You have to choose theta values for which the cost is minimum. So in this case, theta naught should be 4 and theta 1 is equal to 0.6, which is the minimum cost. So therefore, we can write the equation as y is equal to 4 plus 0.6 into x. It is as simple as that. So there is an algorithm called gradient descent algorithm. It facilitates estimation of parameters automatically that minimize the cost function. We'll discuss more about it in the next session. So what we discussed so far is, we try to take some simple example of linear regression, and we assumed the theta naught values and theta 1 values and found out the cost. And after some time, we are able to find out which combination of theta naught and theta 1 gives the minimum cost, and those parameters should be used for modeling the given problem. Dear viewers, it's a pleasure talking to you. If you like the video, please press the subscribe button. It is no cost to you, it's absolutely free. It will definitely motivate me to do more and more videos. That's all for now. Until we meet next time, bye-bye. Thank you.